Hey everyone, I'm Bruno from MOVEdot. Welcome to episode 7 in our tutorial series, where we're developing a sports car together. So far, we've studied many aspects of VI-CarRealTime independently throughout the series. Today, we'll apply that knowledge to study the vehicle as a whole, as we develop an electric version of this sports car. We'll be looking at many of the tests and metrics used at the same time, and discuss multi-parameter investigation, showing you how VI-CarRealTime can be used as a tool for efficient vehicle development. We'll be looking at many of the tests and metrics covered, but now all of them at the same time. And we'll discuss multi-parameter investigations to show you how VI-CarRealTime can be used as a tool for efficient vehicle development. If you want to learn more about the methodology used here, you can watch a previous webinar of ours on vehicle development, which is linked in the video description. Now we can start designing our electric sports car. Let's begin. As usual, let's start by loading the Track Car tutorial session from the File menu. Let's create a backup of the previous version of the model by right-clicking it in Build Mode and cloning it. Call it Track Car EP06, select the Track Car database and confirm. Select the clone's main folder in the tree view, save all, and delete it from there. The transition to an electric car brings many challenges. We will focus on how it affects handling and performance. Luckily for us, the sports car we based our track car on has an electric version itself, and we can use its powertrain and chassis for our needs. One of the most significant differences will come from the all-wheel drive nature of this powertrain that, when paired to electric motors that produce a lot of torque at very low RPMs, means we can expect great low-speed acceleration performance. Due to the added weight of the battery and smaller motors compared to the thermal engine, the center of mass significantly changes and load spreads differently between the front and the rear axle, bringing the center of mass lower and 6% forward, in this case, influencing balance. On the other hand, the batteries are very heavy, increasing the weight of the vehicle by around 50% when compared to the combustion model, as well as rotational inertias in all axes, so we can expect this extra mass to induce some performance loss. You can now download the electric track car file in the description and unpack it. It contains a new database for the electric track car that you can move to the same folder where we're keeping our combustion track cars database. To load a complete models database into CarRealTime's work session, expand the Edit menu and select Preferences. Select the Database tab and click Add New. Then, navigate to the database folder we just moved, select it, and click here to add it to the session. Let's now load the model into Build Mode and take a look at it. Let's select its body subsystem and look for the mass and inertia properties. Currently, this model is essentially the same as our combustion track car, including all of the same upgraded components, but starting from the heavier electric sports car body. On top of that, it includes upgraded brakes to deal with the new mass properties, but nothing else was done to rebalance the car around it. The powertrain subsystem was also replaced altogether. It is exactly the same as the one that comes standard in the electric sports car, and we can observe the types of settings available for it in VI-CarRealTime. Here we can change the general powertrain's layout, as well as add and remove main components. In the diagram to the right, we can click a component to navigate straight to the tab where we can adjust its individual properties that go from torque mapping and torque reactions to controllers and strategies like, for example, for gear shifting, traction control, and torque vectoring. It's also possible to represent the effect of an individual component's mass and its elastic connections to the chassis. When activated, such rigid bodies are framed in blue. Otherwise, their mass will be rigidly connected to the body. The settings available vary with the component's type. Properties for electric motors are different to the settings available for internal combustion engines, for example. For more details on all the possible component combinations and available settings, you can check the help file, available in the main menu. We will keep the electric powertrain unchanged, so let's move on. Everything else in this model is exactly the same as in the latest version of the combustion track car, meaning all of the tuning we did to it throughout the series may not work very well for the electric version, because of the severely different mass properties. Because of this, we will run the new electric track car in some of our previous simulations to analyze how we should tune it to make it balanced too. In test mode, duplicate the following tests 3 times. The test in the constant radius fingerprint, where we analyzed understeer gradient and roll gradient. The test in the step steer fingerprint that allows us to study lateral acceleration, response time, and yaw rate overshoot. Let's also use our max performance test so that we can use the lap time at our reference track as a KPI. Make copies of our comfort tests too, both the speed bump and the rough road ones, as well as the post-rig test, from which we will get our overall damping performance index. And finally, the double lane change test we used in the last episode. For the first of each group of copies, let's change the test model to track car from episode 6, as it will set our baseline performance that we will compare the electric version to. Also rename the tests to refer to this vehicle to make the results easier to identify. Then, let's assign the new electric track car to each second copy and rename them accordingly too. Finally, assign the original sports car for each third copy and rename them to reflect that. These results will serve to give a general idea of how far we came throughout the series, while providing a more meaningful range for the data we will generate. Let's add the letter S when naming them, because we already have some tests for which the sports car was assigned to, and we can't name 2 of them exactly the same. We need to perform one final adjustment to one of the groups of copies so that the data is comparable. Find the step steer tests, and, for the one where the track car from episode 6 will be used, set the steering angle to 72.5 degrees. For the one using the electric track car, the steering value will be 70 degrees. And for the original sports car, the steer value is 59. According to the standards we're using here, these values are set so that the car sustains 0.4 G of lateral acceleration after the steering input is applied. And finding these values is an iterative process. We're providing the final values immediately for the sake of practicality. Everything is now ready for us to run many simulations at once, one of the great possibilities allowed by VI-CarRealTime. It may take some time to process everything, so before we start, let's select our fingerprints and save their settings, as well as the work session itself. With that done, select all of the events we just created and click play to start the simulations. When all simulations are ready, we can head over to review mode to select each grouping and plot their results in the animator to see how the 3 cars compare, one metric at a time. For our convenience, let's observe all of the results at the same time in a single plot, which you could do yourself by post-processing the simulation results files that are available within the working directory. Right away, we can observe how far we came from the original sports car we based our development on, as both track cars score better than it in most metrics. The combustion car is the fastest to lap the reference track, but the electric model is not too far behind, especially when we consider the huge 22-second improvement we had over the base model. If we focus on the track cars only, we can observe how the different mass properties affected handling. Despite being heavier, the electric track car shows less body roll than the combustion model due to the low center of mass. While sharing the same setup as they are now, the understeer gradient result suggests these cars behave differently, with the electric version maybe the most neutral among them. The lateral response for the electric version also seems to be faster, which could be a consequence of the lower center of gravity, but it comes together with a severe increase in yaw overshoot. This is a side effect of the increased inertia, which is also connected to why the electric version achieved lower speeds in the double-lane change test. In terms of comfort metrics, the combustion track car seems to offer the harshest ride among all three, while the electric version seems to outperform even the original sports car in the seat impact test, what may be another benefit of its greater body inertia. If we look at the tests a little closer, by checking each of them individually in review mode, we can notice more details from how the car behaves during the maneuvers. In the max performance event, for example, we can see instances where the electric car shows sudden mid-corner oversteer moments, leading to slides that seems to slow it down when compared to the combustion car's performance in the same points. If we tune the electric car so that it scores closer to the combustion one in these key metrics, they shall behave similarly and will be effectively equivalent in terms of time attacking potential at typical road tracks. And we will perform this tuning according to the methodology presented in the seminar linked in the description, by first recalculating a series of key parameters to suit the new mass properties and later fine-tuning the remaining ones by investigating for an optimal result. Starting with the springs, since the new electric track car's suspended mass properties are so different to those of the combustion track car it was based on, its springs must be redesigned to fit this change. This is a basic modification that guarantees our suspended mass moves in a controlled manner with road irregularities. We will do it by increasing the spring stiffness relative to each axle's weight increase, by matching the same natural frequency as the previous car, and, as a consequence, providing a similar ride experience. Let's apply our results for this study by heading over the front suspension subsystem in build mode, expanding the springs tab and changing the following parameters to the values on screen. Now, let's do the same for the rear suspension subsystem by changing the same parameters to these values. Note how we balanced the rates so that the scaling factor could be reset to 1. This is not necessary for the simulations to run correctly, but doing so will make data interpretation more straightforward when it comes to using them as a reference to design and manufacture the physical springs. Then, we will adjust the anti-roll bars to rebalance the lateral load transfer distribution, which can be analyzed in the constant radius cornering test. To do this, navigate to the anti-roll bar tab in the front suspension subsystem and change the rate from 15.5 to 12 Newton per millimeter. And for the rear anti-roll bar, change the rate from 41 to 45 Newton per millimeter. For the dampers, we will use the same components as before, meaning the property files will not be changed, but we will recalculate the damping ratios through the scaling factors to suit the other new properties. In the front suspension subsystem, change the front damper's scaling factor to 1.68. Then navigate to the rear ones and change their scaling factor to 0.65. These main calculated changes shall lead to a more balanced car right away, with similar ride behavior to the latest version of our combustion track car, that we already judged to be at a fine state. We have a final set of parameters to tune before we can consider this process finished. They are the wheel angles, which we will define simultaneously using a multi-parameter investigation. Before we do that though, we performed individual investigations for each of them to identify the range where they are sensitive to change and the limits over which undesired behaviors would start to show, like overall performance losses or stability issues. Doing this allows us to run a narrower but more meaningful investigation when analyzing their combined effects. Let's begin setting it up now. In test mode, make another copy of the original step steer and constant radius we used in episode 2. For both of them, change the model for the electric track car. Rename them so that they're easier to find. We will do this by mentioning the focus on the electric car and adding a 2. Save the fingerprint, select the new tests, and run them once. We will need a series of custom processing scripts for those investigations, which you can download from the description too. Extract and move them to the scripts folder we created beside the working directory. When the simulations are ready, head over to the Investigation tab. In the bookshelf, find the constant radius one and add it to a new investigation. Select it in the tree view and promote the front left and front right toes into factors. Put them both in group 1. Name them toe F left and toe F right, respectively. Set their delta type to absolute and set their interval from -1 degree to 0 with 3 steps. Now promote the rear left and right toes into factors. Put them both in group 2. Name them toe R left and toe R right. Set their delta type to absolute and set their interval from 0 to 1 degree with 3 steps. Also promote the front left and right camber angles to factors. Set their group as 3. Name the first of them camber F left and the other camber F right. Delta type absolute. Make the lower limit -4 and the upper limit -2 with 3 steps. And promote the rear left and right camber angles to factors. Set their group as 4. Name them camber R left and camber R right. Delta type as absolute, with a lower limit -4 and upper limit of -2, also with 3 steps. Add the first response and name it US at 0.2 G. Set its function to custom computed value and look for the following output channels in order: chassis, accelerations, lateral, tire, lateral slip with lag, left 1, tire lateral slip with lag, left 2, tire lateral slip with lag, right 1, tire lateral slip with lag, right 2. And call for the custom Python script called us02.py. Add 3 more responses that will have the same settings as the first one, but will be named US at 0.6 G, at 0.8 and 1.2, and assign the corresponding US Python script to each of them. Set this investigation's simulation mode to inherited from event, give its output folder a unique name, and make the simulation full factorial. Go on the bookshelf again to find the new stepsteer event and add it to a new investigation. Select it and promote the same candidates to factors as we did before by following the data that is on screen now. This investigation will use 3 responses. Add the first one and call it yaw overshoot. Make its function custom computed value and browse for the following output channels: time, chassis displacements roll,
driver demand steering, chassis velocities yaw, and chassis accelerations lateral. And give it the step yaw over Python script. Add the second response and call it LART, which stands for Lateral Acceleration Response Time. Set it as custom computed value, add the same output channels as before in the same order. Browse for the step LART Python script, add the last response and call it AYSS, referring to the lateral acceleration sustained when the car reaches steady state after the maneuver. Make it custom computed value and add our same previous output channels. And select the step AYSS Python script. Set the simulation mode to Inherited from Event, name the output folder, and select Full Factorial Simulation. We're about to run a large amount of simulations at once, so save them and also save the session before we proceed. Then select both of the new investigations in the preview and run them. This is one of the strong points of VI-CarRealTime. Technically, we could investigate all of the handling parameters at the same time. The time required to run such investigations grows exponentially with each new parameter we include, but gives us a very optimized and scientifically backed solution. Each of the investigations we just configured will run 3 to the power of 4, or 81 combinations, and it serves as a good illustration for the process. It's a narrowed down version of the more detailed investigation we ran when developing this example, that had wider ranges and a slightly larger resolution, resulting in 1,764 combinations each. When the investigations are ready, select the constant radius 1 and open its design space to see the results. Here, let's go straight to the bottom to study the plots. It may look a bit crowded at first, but it's pretty straightforward once we know what we're looking at. We have a list of all 81 combinations here, and this region describes the toe and the camber each combination is using in each axle. The 4 columns to the right are the results themselves, and they describe a simplified understeer gradient curve for each combination. This is one of the key metrics where we identified our electric car needs work. In our previous evaluation tests, we found out its understeer gradient was at around 0.85 degrees per G. Very different to the combustion version that scored a bit over 1.05. The results we just got show that we can get this metric very close to our target if we adopt wheel alignment values near what the solutions around this area have. If we highlight versions 22 and 25, for example, we can note that both of them share a front toe of -1 degree, rear toe of +1 degree, front cambers between -2 and -3 degrees, and -4 degrees of rear camber. Adopting lower front camber should lead to a weakened front axle at the limit, and could be seen as a trade-off between front axle grip and overall balance, where we're effectively slowing the car down to guarantee more predictable handling. We can close this report now. Select the step steer and open its design space with results. This investigation contains metrics focused on response. Our goal here is to reduce yaw overshoot that was previously at around 10% without sacrificing much of the great performance we saw in lateral acceleration response time. Right away, we can see many combinations would do the opposite of what we want, causing yaw overshoot to increase above 10%. On the other hand, combinations 19, 22, and 25 are the ones that better suit our goal here, while still providing quick response. All of these have -1 front toe and +1 rear toe, while their front camber is in between -2 and -3, and rear camber is between -3 and -4. With these results at hand, we can close the report and go back to CarRealTime. All of the results that we identified as satisfactory pointed towards the very same tow values, thus we will apply them to the car directly. For the front camber, both investigations delivered the best results in between -2 and -3. So we will choose -2.5 degrees as it sits perfectly in the middle of them. The rear camber results analysis is a little more complex. We also have a range of acceptable solutions between -3 and -4 degrees, but going lower seems to reduce yaw overshoot, while also being a necessity to guarantee we reach our target for the understeer gradient. So we will stick to -4. To implement these changes, let's go to Build mode, select the front suspension subsystem, and within the Wheel Angles tab, change tow to -1 degree, which is tow out, and camber to -2.5. And in the Rear Suspension Wheel Angles tab, change the tow value to 1 degree of tow in, and camber to -4. Our electric track car is fully updated, and all we have to do now is rerun the same series of tests we created for it earlier in the episode to check if it actually evolved as we intended. If we would add these new results to the plot we had earlier, we would see this. The fine-tuning we did was enough to bring the understeer gradient a lot closer to that of the combustion car. The intended reduction in yaw rate overshoot is also there. Despite still quite far from the combustion car in this metric, we managed to bring the electric car a bit closer to it. This is a downside of the extra mass, added by a typical electric powertrain and a compromise we will have to make. Still, we accomplished all of these improvements with no loss in lateral acceleration response time, and with both cars displaying very similar roll gradients in a desirable level for a sports car. The tuned version got a little harsher in terms of ride, but is still in the acceptable range. And it is even better than the original sports car in terms of impact absorption, which was an expected benefit from making the car heavier. And all of that came accompanied by an improvement in lap time that put the new car within less than a second of its combustion version. To wrap up our analysis, we can conclude that, despite some persisting characteristics inherent to the electric powertrain, our development session did make the new car perform very close to the combustion model and also made them effectively identical in time attacking the reference track. And so, it was a success. Today, we created an electric variant of our track car while using many features of VI-CarRealTime at once, performing complex analysis as we practiced vehicle development methodology. While doing so, we learned how to load a complete model into VI-CarRealTime, overviewed the resources available for powertrain modeling, analyzed the vehicle as a whole, relying on multi-parameter investigations for optimization that we used to discuss about the between traditional battery-based electric cars and ICE-powered cars. Stay tuned for the next and final episode in this series, where we will run driver-in-the-loop tests to further analyze each version of the vehicle we created and discuss how each step we took in development affected the car's performance and handling. With such information at hand, we can apply all we learned about VI-CarRealTime in a final round of fine-tuning to hopefully extract every little bit of potential available in our track cars platform. I will talk to you soon.